Next, I want to talk about models of systems, and this is a way of taking the complicated real world as we have it and trying to simplify it in a way to understand it. So this would be, say, Friant Dam. I don't know if this, yeah, it's pretty close. Friant Dam and Millerton Lake. And if you, say, wanted to know how much water is in Millerton Lake, a reservoir behind a dam, and, you know, let's say this is your new job. You need to know how much water is in Millerton Reservoir. Now, you might think, well, heck, how do I know? Well, maybe you know how much is in there to start with when you start your job. Then what you need to do is know, well, what do I need to keep track of? You need to keep track of inputs and outputs. Inputs, adding water to the reservoir, outputs, taking away water. Maybe one thing you need to know is how much is flowing in from the river. That's an input. The other thing is, how much are you losing from evaporation? That's an output. And then also how much is just being released out of the dam. That's also an output. If you know, you can turn this into some type of a math problem where you see how much is coming in, how much is going out, and that will allow you to help understand the levels of the reservoir. So let's talk about these things. So models are a simplified way of looking at a complex real thing. And this is a pretty general maps, globes, these sort of conceptual models. These are just taking a really complicated real life thing and trying to simplify it in a way to understand it. If you think of a map of the world, you might look at a map or a globe. So this is a globe, right? This is a model of the Earth. It's not the real Earth, but it has certain properties. It shows you where things are, it has the approximate size and shape. It shows the different features that are there. And so, while the real Earth is a complicated thing to understand, a model like a globe here is a way of helping you kind of visualize and understand it. Systems are kind of a similar concept, but we can go a little deeper and say that they are a set of things that work together. And they have variables. They have inputs and they have outputs. So in the case of our reservoir, it has variables. It has inputs like inflow and outputs like evaporation and outflow. And when it comes to these systems, like say this reservoir, we look at how well they're in balance. Do they change or do they stay the same? If the inputs and the outputs were always equal to each other, then the reservoir level would never change. That would be what's called a steady state equilibrium. It's very rare in nature, or even in something like a reservoir. So if you go to Millerton Lake, sometimes it's higher, sometimes it's lower, but it may be the case that it's in what's called a dynamic equilibrium. It goes up, it goes down, but it's changed within a range of tolerance. There's a high level and a low level, and it kind of moves in between there. Now, what maintains equilibrium are different feedbacks. So let's say in the case of our reservoir, levels got too high, we released water out of the dam. That brought levels down. Then levels got too low, we stopped releasing water and let it fill back up, and so on. So you know, water's coming in, water's going down, and these feedbacks kind of keep it from either overtopping or becoming empty. You can also have positive feedbacks, and what these are a little bit different. These are when something occurs and causes things to kind of flow out of control. One example I sometimes use in my in-person classes, let's say during the holidays, I eat too much cake and pie and I gain some weight. I gain a fair amount of weight, or under quarantine, let's say. So let's say I change my diet and exercise more. That would be a negative feedback that would send things in the other direction. Probably the less likely scenario of me losing too much weight. I might kind of change my diet again or do something different that would cause it to rise again. And I might fluctuate between these different levels, but I would maintain this sort of dynamic equilibrium, right? Let's do the positive feedback. Now, one thing I really want to highlight here is that there's nothing good about negative, nothing feedback, and there's nothing bad about negative feedback, I should say, nothing good about positive feedback. It just has to do with the direction. Negative feedback reverses things. Positive feedback causes them to increase. Let's take the pie example. Let's say during the holidays I eat too much pie, but then I get kind of bummed about it, and so I eat more pie and get more bummed about it, and so on. You know, it's kind of like what started it causes it to continue at an increasing rate. All right, so negative feedbacks, what they discourage feedback. So like your thermostat, let's say, you know, you might set it so if it gets up to a certain temperature, the cooler comes on, and below a certain temperature, the heater comes on. Those would be negative feedbacks that would maintain a constant temperature in your house. A positive feedback is the opposite. It's nothing good about positive feedback. It's just about the direction. It's like what we call a snowball effect. It starts and then it increases and increases and increases and increases. So going back to this example, you know, eventually, what would happen, you know, in terms of my health or well-being if I kind of continued on the slope? Well, you know, something bad would happen. You might get sick, or you might be in ill health, and that's called a threshold. That eventually, as you know, if the positive feedback is spinning out of control, there will be a point at which, you know, the whole system changes and resets, and that's called the threshold. So negative feedback counteract each other. They keep things in balance. Positive feedback reinforces the change, causes it to keep moving in a certain direction until it reaches some threshold condition where the whole system changes dramatically. And maybe a better example would be looking at something called melt ponds, a physical geography example. And move that down a little bit. And so this is in Greenland in June of 2001 and in June of 2003, where in between here it got incredibly warm. And it might be hard to see, but you see these little, there's a bunch of little dots here, and these are something called melt ponds. And what they are is that if it gets warm enough, some of the water might melt, some of the ice might melt into little depressions. And so instead of ice there, now you have liquid water. Now these melt ponds with the liquid water are darker than the ice. So ice stays cold a lot of times because it's very bright and reflects sunlight. However, these melt ponds are darker. They have less, what we call albedo, less reflection. So they absorb more of the sun's warmth. They get warmer. So they get warmer, they melt more ice, make more melt ponds. Those in turn melt more ice, make more melt ponds, and so on and so on and so on. If you kind of think about this, the fact that you have these melt ponds makes more melt ponds, makes more melt ponds. That's an example of positive feedback. Now, the threshold would be that eventually, if this keeps going, that you could just lose all of the ice and just there would be no more ice to melt. And that would be the threshold condition.